Let us start. So we will continue the discussion what we had, that is the motion under central orbits. So in this, right, so two important fundamental tools what we need is, so we need to understand something called the pedal form, right? So we need to understand what is this pedal form is. So there are different ways of expressing an equation. So that is, either you may express in the form of Cartesian coordinate system, you may express as polar coordinate system, or you may express as, that is the pedal form. Because actually in the central orbits, right, so this is convention most of the times actually. So the questions are going to be asked in the form of the pedal. So the pedal equation is nothing but for any curve. Suppose if you are able to express the location of the particle in terms of the radius and the perpendicular distance to the tangent. That is, suppose if I take a point at this location, the radial distance for this is this one. So this is the radial distance. So this length is r. Now if I draw a tangent at this location, so this tangent is going like this. Now if I draw a perpendicular from this pole, so this point is called as the pole, and this is the perpendicular distance. Of the tangent from the pole. So this length is called as the pedal, P. And this angle is usually treated as an angle phi. So this is the angle phi, and this angle, which is nothing but the angle with respect to the x-axis, so this angle is usually treated as psi. So this is going to be used for the, so that is the slope. So this angle actually we consider for the slope, and this angle actually we consider in the calculation of the pedal length P, and this angle is from the initial line. If it is making an angle of theta, so this angle theta and r. Suppose if you express r as a function of theta, so this is what we call as the polar coordinate system. Suppose if you express P as a function of r, then this form is called as the pedal form. Got it? So this P value we are expressing as a pedal form. So this is the curve what we are talking about. For this curve, at any point if I consider, that location is going to be the r. So this location we are expressing in terms of this pedal and this radius length. So in a two-dimensional coordinate system, we always need two different coordinates to represent a fixed point or any point. So that can be either x comma y is one form, or r comma theta may be one form, and r comma p may be another form. So everything is a different coordinate system for us. Now out of all these coordinate system, based on the convenience and based on the application complex level, so we are going to use different kinds of coordinate system. Now what we are going to discuss here, it is the r comma p format, which is nothing but the pedal form. So there are a lot of animations that are going to be there in YouTube or actually maybe in web, right? You just search for the pedal form. There are different kinds of animations how to trace a curve with the pedal form. So that will give you more insight into that. But actually we are going to use certain relations based on this pedal. So those relations actually I am going to derive first, and then actually we will derive the central orbit equation in the pedal form and the peripheral velocity in the form of the pedal, right? So these are the things actually we are going to do it. So I hope you understood what is a pedal form. Got it? So if you understand the pedal form, now actually there are different kinds of relations actually that we are going to discuss. So we'll do one. Let us say, so this pedal, first you draw this diagram. I'm going to change this diagram for a better understanding purpose. First you note down this. So this is Cartesian, and this is polar, and this is the pedal. But essentially we are trying to convey the same information in all the three different kinds of coordinate systems. Done? Okay. So now those relations what we are going to discuss are so one is r d theta by ds equal to sine phi. So this is one relation, and 1 by p square equal to 1 by r square plus 1 by r power 4 into dr by d theta whole square. So this is another relation what we are going to use. Now actually we need to understand how these relations are coming in case of pedal, right? So this is, suppose if you draw this coordinate like this, and let us say this is the curve, and then this is the r, which is the initial value of r. Then after a change of r from r plus, so r to r plus delta r, so this is the change in length. So this is r plus delta r. Now this is at an angle of theta. Now actually this angle changed for an amount of delta theta. Now this is the r value, this is r plus delta r. So these coordinates are r plus delta r and theta plus delta theta. So these are the new coordinates, and initial coordinates are r comma theta are the coordinates. Now this angle, suppose if I join a line here, and this line we call as ds. Why we call as ds is nothing but the arc length at any instant. So whether I specify specifically or not, as and when ds occurs, you can treat that as the arc length. Now I call this length as the arc length because actually we are going to use the calculus where the length delta s tending to 0, which essentially means that this r plus delta r overlaps onto r. That means this delta theta tending to 0, then this line coming and matching on this line. Then this small portion as if like it is a straight line. So for an approximation purpose actually this arc can be treated as a straight line if delta theta tending to 0. But for our understanding purpose, if I draw a bigger line, that will be far easy to understand rather than drawing almost closer or at the 0 distance, right? So for this arc actually I am approximating this arc length as ds, this one, where ds tending to 0, this straight line and this arc are one and the same, and that time actually delta theta will tend to 0 and delta r also will tend to 0. So now actually based on this understanding, if I draw a perpendicular here, so let us call this as n and this point as p and this point as q, then pq is the arc length, or pq straight line also we can call as the arc length for approximation purpose, and then let us say this angle is phi, and then so if I want to calculate tan phi, so first actually let us prove the first relation. So first relation actually for this actually, so this is r and this is r plus delta r and this is ds. If I apply the sine rule, then sine rule says that so a by sine a equal to b by sine b equal to c by sine c for any triangle. Now for this triangle of, for triangle OPQ, if we apply sine rule, then so ds by sine delta theta is equal to ds by sine delta theta is equal to r by sine phi. So from this relation sine phi equal to r into sine delta theta by ds, right? Now here actually we need the relation r d theta by ds should be equal to sin phi. So sin phi is equivalent to that one. Now here actually delta theta and delta s actually tending to 0. Now for this relation, if I divide with delta theta on either sides, I'll just write it here. So here actually, so sine of delta theta by delta theta as delta theta tending to 0. So this is going to be 1. So r divided by ds by d theta, you can call this as this is delta s by delta theta where delta theta tending to 0, you can call this as ds by d theta. So from this r d theta by ds, so this is equal to sin phi. So this is one important relation. So this is applicable for any kind of curve. Got it? So this is where ds is the arc length and this is angle between r and the tangent at r. So this is the angle. Now actually this is the angle. As delta theta tending to 0, this can be approximated as if like a tangent which is drawn at this location like this. So this is going to be phi. So if delta theta tending to 0, I hope you understood this concept. This angle I can draw it here as delta theta tending to 0. Got it? So this angle and this angle are one and the same. This is the macro level and this is the micro level. So if I join these two together, if I draw a tangent at this location, this angle is phi. So that's what actually we are trying to approximate here. So I hope you understood. You got a clarity on this? How this r d theta by ds is equal to sin phi. Any questions on that? Got it? So you can note down this. So this relation and this relation also we are going to use it. Now I am going to derive this relation for the same diagram. Okay. Now for the second relation, so if you want to calculate tan phi for that relation, tan phi equal to Pn by Qn and Pn is this length. So this is being r and this length Pn can be expressed as, so this one and this is this is a perpendicular here. So this length is On is r cos delta theta and Pn will be r sin delta theta. So this is r sin delta theta and then On is equal to r cos delta theta and we need Qn. Qn is equal to OQ minus On. So OQ can be expressed as r plus delta r minus On can be expressed as r cos delta theta. Now this is delta r plus r times of 1 minus cos delta theta and this is delta r plus r times of 1 minus cos delta theta can be expressed as 2 sin square delta theta by 2. 2 sin square delta theta by 2. Now this is Qn. So for tan phi Pn value, so that is r sin delta theta divided by Qn value is delta r plus 2r sin delta theta by 2. Now if I divide on top and bottom by delta theta, so this is r sin delta theta by delta theta divided by delta r by delta theta plus, so 2 times of r into sine delta theta by 2 divided by delta theta. This 2 I can bring it to the bottom here. Right? So 2r sine delta theta by delta theta. Sorry, this is sine square, right? Yeah. So one sine here and here again sine delta theta by 2 is there. Now this relation, if you take the limit delta theta tending to 0, then yeah, Pankaj, yeah, so I just corrected. So this is delta r by delta theta. So this is r into sine delta theta by delta theta. So numerator is going to be r, because actually since sine delta theta by delta theta is equal to 1. Now if you replace it here, so this is numerator is going to be r and the denominator is, so limit delta theta tending to 0 delta r by delta theta. So this you can replace as dr by d theta. And then r times of this is 1 and as delta theta tending to 0, this is going to be 0. So if this is going to be 0, we left with nothing here. So this can be replaced as r d theta by dr. So this is the tan phi value. So this relation we need to remember. So two relations. One is r d theta by ds is going to be sin phi and r d theta by dr is going to be tan phi, where phi is the angle that is made by the tangent to the radial. So this is the radial and this is the tangent and this is the angle phi. And this angle is usually treated as psi, and this length which is drawn at a perpendicular distance to O, and this value is going to be P. Now actually we are going to play with this phi and this P and this R. Got it? I hope you understood these relations. Based on these relations, I am going to bring this relation. Got it? Understood? Or do we have any questions on this? Okay. So, so this relation now actually okay. So keeping this in mind, so we know that so 1 by p square and p value. So for this triangle, p can be treated as r sin phi. P is the value of r sin phi. And this length actually r cos phi, this anyway we don't need it, but this pedal length we are very much interested. Now 1 by p square can be written as 1 by r sin phi whole square. So from this relation, cosecant square phi divided by r square, and then 1 by r square into cosecant square phi can be written as 1 plus cot square phi. So this value is going to be 1 by r square times of 1 plus cot square phi. You can replace dr by r d theta. So dr by r d theta whole square. So this is 1 by r square plus 1 by r power 4 into dr by d theta whole square. So this is this relation. So 1 by p square equal to 1 by r square plus 1 by r power 4 dr by d theta, and this relation is universally valid for any kind of curve in polar form. So valid for all the curves in pedal form. So this one also and that one also. Got it? So this relation actually we are going to use for deriving the central orbit in the form of the pedal. At the same time, peripheral velocity also is going to be dependent on this relation. So these are the fundamentals that are needed from the coordinate system to understand the central orbits to a deeper level. Any questions on this? Okay. Fine. So let us move to our discussion. r d theta by ds is equal to sin phi, and r d theta by dr is equal to tan phi, and 1 by p square equal to 1 by r square plus 1 by r power 4 into dr by d theta whole square. So these are the three relations. What is the use of the pedal form? So pedal form is actually, see, so the question is actually as if like what is the use of polar coordinate system, right? So this is actually one form where you can express the curve, and for certain kind of problems actually this is easier. Now actually here in our gravitational analysis, right, there actually we are going to use this pedal form for much more easier and convenient way of expressing the peripheral velocity. At the same time, the central orbit also you can express in the form of the pedal form, so that actually we can easily find out the path of the orbit. Got it? So these are the advantages, and the research was done mostly on this pedal form towards the gravitation, hence we are learning this. Got it, Pankaj? Okay. So now actually based on these relations, right? So the relations are okay. So first we derive the peripheral velocity of the planet. So if you want to derive the peripheral velocity of the planet is, so the question comes from this fact that here, so the planet rotates in an elliptical orbit like this. So this is the ellipse actually where the planet is trying to rotate. Now here actually in the previous classes actually we have derived that the velocity of the planet has to be dependent on the position vector. Let us say this is one focus where the sun is located, and this is another focus. Now at this location actually the sun is located. Now if the planet is here versus if the planet is here, I explained earlier the rate of aerial velocity, right, is going to be constant for any kind of central orbits. So the rate of aerial velocity, we mean the planet actually trying to move from here to here. Let us say it took 1 day, then actually it is covering an area of this one. So the radial vector is trying to cover an area of certain quantity. The same quantity is going to be covered when it is moving from here to here. Now here if you notice, to cover the same area, it has to travel for more distance. It has to travel more distance. To cover the same area, it has to travel very less distance. And I explained the logical reasoning also. So when the planet comes here, then actually the center of attraction will be very, very high, because actually the planet and sun are very close to each other. So the attractive force or the gravitational force is very high at this location. So here actually the gravitational force is less. So if the gravitational force is less, then actually even if it travels with a lesser velocity, the centrifugal force is sufficient enough to balance the gravitational force which is attracting towards the sun. So that means the outward centrifugal force for the planet, that is given by mv square by r, and the inward centripetal force given by the sun, which is called as the gravitational force. So these two are less and are going to be balanced to travel in the elliptical orbit at this location. Now here the attraction of the force is very high. So the centripetal attraction. So this is the gravitational force, and this is going to be high at this location. So if it is high, then actually to balance the centripetal force, it has to travel with more velocity. So it has to travel with the more velocity, so that mv square by r, which is the centrifugal force, is very high, so that the velocity is more to balance the centripetal force by the gravitation. So the only option for the planet is it has to increase its velocity at this location, and it has to decrease its velocity at this location, and in between actually it keeps on changes its velocity based on the position. Now as it is changing its velocity, we should be able to understand what will be its velocity at any position vector. So that velocity we call as the peripheral velocity. So at any location, suppose if I take it here, this is the tangential velocity at this location, this is peripheral velocity. Why we call as peripheral velocity is, there is another velocity called the angular velocity. Angular velocity is the rate of change of angle. So when it is trying to rotate about this point, the angle is going to be changed with different kinds of angular velocity at this different locations. Now, depending upon the angular velocity, the peripheral velocity is also be changed. So the peripheral velocity is when it is traveling with this length. So how much time it is going to take it is nothing but the peripheral velocity. So this peripheral velocity we will be able to calculate in the form of the pedal. Now here, when we are trying to calculate it here, so the fundamental condition in the entire process of this planet rotation is one single concept, that is called the angular momentum is going to be a constant. So that is the fundamental rule. Is constant for any central orbit. So this I already proved. So for any central orbit, right? So I proved that earlier. So from the general relation of any planet moving in a plane, we proved the relation d square r by dt square minus r into d theta by dt whole square, and this is the radial component of acceleration, plus r into d square theta by dt square plus 2 times of dr by dt into d theta by dt, and this is the theta cap component of the acceleration. So this is the acceleration of any planet moving in a plane. Now for a central orbit, actually we proved that this velocity is always equal to minus p, and this acceleration is always equal to 0. So this acceleration is going to be minus p, and this acceleration is going to be 0 for any central orbit. So central orbit, we mean the line of action of the attraction has to be always passing through a single point. So this is the single point. The planet, whether it is here, it will always attract in this direction. If the planet is here also, it will try to attract exactly in the same manner, that is towards this particular point of focus. And even if the planet is here, it will attract in this same manner towards this particular point. That means whatever may be the location of the point, or whatever may be the location of the planet, the line of action of the attraction force always has to pass through the sun. And this kind of force we call as the central force, and the orbit that it is taken by the planet is called as the central orbit. In such cases, there will be only centripetal acceleration. No angular acceleration is going to be changed, is going to be there. So as there is no angular acceleration, then actually this part is going to be 0, and this is the fundamental property of any central orbit. Now this one actually I expressed, actually this is going to be 1 by r times of d by dt of r square d theta by dt, and this is what actually we proved that. So this is going to be 0, and this actually you can express in this particular format, and this is going to be 0 from this relation. So r square d theta by dt is equal to constant. So this constant we call as the angular momentum. So this is the angular momentum. So this angular momentum, so r square into d theta by dt. Now this r into r d theta by dt. So this is r into r d theta by ds into ds by dt. So if I express in this particular format, and this part actually we just derived that r d theta by ds is going to be sine phi. So this value I can replace as r into sine phi into, so ds by dt is nothing but the rate of arc coverage within a time of t. So that means the rate of change of arc length is nothing but the peripheral velocity. So this is ds is arc length, keeping this as the pole. So sun as the pole, as the planet is trying to move in this particular format, then the rate of coverage of arc length is nothing but the peripheral velocity. So this I can replace with v. So where v equal to ds by dt, rate of coverage of arc length, of the path, right? So this is the peripheral velocity. Now r d theta can be replaced with sine phi. So there is one r, and this r d theta by ds can be replaced with r sine phi. So total r sine phi into v is nothing but the angular momentum h. So this is the fundamental relation, where phi is the angle between the perpendicular drawn from the pole to the tangent. Suppose if I take this point, then the tangent is in this particular format and a perpendicular drawn from the pole. So this is the perpendicular length. So this length is nothing but the p. So from this pole, a perpendicular to the tangent, this length is the p. So this p value, so r sine phi is equal to this p value, because so the angle is nothing but arc and then this angle is phi. So this is, let us say this is the point, and then this is the radial distance, and this angle is the phi. So r sine phi will be the perpendicular length p at this location. So this you can even replace, r sine phi can be replaced as p, then it implies pv equal to h, where h is a constant. This is as simple as that. So this level of complex equation you will be able to express in a simple format of pv equal to h, and pv equal to h here, p is the pedal length and v is the velocity of the planet and h is the angular momentum. Now one more advantage is h is anyway constant for any central orbit. That means v is inversely proportional to p. So if the pedal length is more, then the velocity is less. If the pedal length is less, then the velocity is going to be more. So this is a simple relation of v is directly proportional to p, or p is directly proportional to v. Sorry, p is directly proportional to 1 by v. Got it? So p is directly proportional to 1 by v, or v is directly proportional to 1 by p. So this is the simple relation which will bind the planet velocity. Got it? I hope you understood this concept. Understood? Or do you have any questions on this? So PV equal to H is the relation. So where V is the peripheral velocity and P is the pedal length. Now from this relation, so V can be expressed as H by P. Now we have another relation, 1 by P square equal to 1 by R square plus 1 by R power 4 into dr by d theta whole square. Now if you substitute the same relation, V square equal to H by P whole square, then V square can be expressed as H square times of 1 by P square can be expressed as 1 by R square plus 1 by R power 4 into dr by d theta whole square. So this is how actually you can express. Now if you want to replace with another relation, that is, so u is equal to 1 by R, then du by d theta can be expressed as minus 1 by R square into dr by d theta. Now if you square it on either sides, du by d theta whole square can be expressed as 1 by R power 4 into dr by d theta whole square. So this is another relation where you can replace here. And here 1 by R square anyway you can replace as H square times of u square plus du by d theta whole square. So this simple relation you can make use to calculate the peripheral velocity of any planet. Got it? So h square into u square plus du by d theta whole square is the peripheral velocity. Any questions on this? So, and another convention is there is something called apse. Apse we mean here, apse of any planet with respect to the sun is nothing but the farther and the least distance location of the planet is called as the apse. So this is one apse where the planet is too far from the sun, and this is another apse where the planet is too short or actually very close to the sun. So these are the two different places where the apse can occur. So apse meaning the farther and the least distance. And so apsidal distance we mean here the distance from the sun to the planet at the location of the apse is called as the apsidal distance. And another convention is apsidal angle. Apsidal angle we mean the angle between two consecutive apses is called the apsidal angle. So this angle is the apsidal angle in case of a planet rotating in an ellipse. So this is going to be 180 degrees. Okay, so u is just a convention, right? So inverse r actually is treated as u. So if you want to express the equation in terms of r, that will be a little complicated. Because of that, so we have introduced something called u, which is the inverse of r. The differential equation is expressed in terms of u rather than r. So as and when required, you can always replace u is equal to 1 by r or r equal to 1 by u. So this is just to reduce the complexity, nothing more than that. Complexity of the equation. As I told you, right? So research was done more in this particular format of 1 by r and the pedal form. So that's why actually the literature was completely there in these conventions. Hence we are following the same. Got it? Other than that, there is no other importance for this u. It is just to reduce the complexity of the differential equation to a simple form. Got it? So did you note down? So apse we mean, apse is nothing but a point where the planet is too far from the sun. So apse meaning, so this is one point of apse. Apse is the farthest point from the sun to the planet. So in the entire planet orbit, right? So this is the place actually where it is too far from the sun. And if at all there are such kind of places are many, then actually all those points we call as the apse points. Now here the least distance point also is called as the apse, right? So in other words actually, so for this planet orbit, right? So the derivative with respect to r is going to be 0 because actually this is the maximum value and this is the minimum value. So wherever this maximum and minimum occurs, right? Those points are called as the apse. And the distance between two consecutive apse, the angle between two consecutive apse is called the apsidal angle. That means this is one apse and this is another apse. The angle between them is 180 degrees is the apsidal angle. And apsidal distance is nothing but from the sun to the farthest point, distance is called as the apsidal distance. Even from the planet to the sun, which is the least point or the least distance, is also called as the apsidal distance. This is just a convention in describing the problem statements. Got it? Okay. So noted down. So sometimes actually the differential equation of the planet orbit, that is the central orbit value, sometimes it is expressed in the pedal form, the differential equation itself. So that is, so the pedal form, so equation also we will be deriving. So our equation is, that is p by h square plus h square u square is equal to u square plus d square u by d theta square is equal to P by h square u square. So this is the equation of the central orbit. So this is the general equation of any central orbit. So from this actually law of force actually we can express, or actually law of orbit also we can express. So that is u square in plus d square u by d theta square is nothing but the equation of the orbit. Now actually this equation we will express in the pedal form. Yeah, this equation is correct, right? Yeah, that's correct. Okay. So if you are expressing in the pedal form, it is nothing but we are expressing in terms of P and R, this entire equation. So eliminate theta and u. So you replace this with P and R. So for this actually, so this is u square So we have got the relation 1 by p square equal to u plus du by d theta whole square. So this is the relation we have derived, right? 1 by p square equal to u square plus du by d theta whole square. So this equation actually we will try to bring in this particular format. Now let us see. See this. If you take the derivative on either sides, minus 2 by p cube into dp by dp by d theta. So with respect to theta, if you derive it, so this is du by d theta plus 2 times of du by d theta into d square u by d theta square, right? So this is d square u by d theta square into 2 times of du by d theta. Now minus 2 by p cube into dp by so d square u by d theta square you can replace as d theta du by d theta. If you take it out, 1 plus 2 times of d square u by d theta square, you can replace as p by h square u square minus u square. Oh, sorry. So the relation was wrong. Yeah. So this is correct. So 1 by p square equal to u square plus du by d theta whole square. Now if you take the derivative on either sides, minus 2 by p cube into dp by d theta is equal to 2u du by d theta plus 2 times of du by d theta into d square u by d theta square. Now this value is going to be, so 2 times of du by d theta, if you take it out, then we left with u plus d square u by d theta square. And then this is minus 2 by p cube into dp by d theta. Now if you convert this into minus 2 times of p cube into dp by dr into dr by d theta is equal to 2 times of du by d theta into u plus d square u by d theta square. So dp by dr into dr by d theta. So dr by d theta value you can express as So there is one more mistake here. Sorry. Yeah. So this is u plus d square u by d theta square is equal to p by h square u square is the equation of the central orbit. From this relation, actually, we tried deriving in this particular format, and then here actually we got the relation u is equal to 1 by r. So du by d theta you can express as minus 1 by r square into dr by d theta. So from these relations actually we can express now. See this du by d theta you can replace with this value, and then u plus d square u by d theta square you can replace with this value. Now if you put it here, so this value is going to be 2 times of minus 1 by r square into dr by d theta into p by h square u square. P by h square u square. This is going to be minus 2 by p cube into dp by dr into dr by d theta. So from this relation, this dr by d theta and this dr by d theta will cancel out. This minus and minus will cancel out. 2 will cancel out. And then 1 by p cube into dp by dr is equal to p by h square u square and 1 by r square. So 1 by p cube into dp by dr is equal to 1 by r square h square u square p by. So this is the equation. Yeah, that u square actually you can eliminate as, so r square h square u square. Yeah, first you note down this. I am going to erase it and then further simplify it to one more step. So 1 by p cube into dp by dr is equal to, so 1 by r square can be written as u square into p by h square u square, since 1 by r square equal to u square, p by h square. So dp by dr is equal to into 1 by p cube is equal to capital P by h square. But actually make the difference, this is the acceleration and this is the pedal. So this difference actually you have to make a note of it. Got it? So this P is the centripetal acceleration or the central acceleration. Fine. So this is how actually, this is the pedal form of the same differential equation what we have expressed as, that is P by h square u square equal to u plus d square u by d theta square. So this relation and this relation are one and the same, but this is in the polar form and this is in the pedal form. That's all. Got it? Understood? Okay, so you note down one problem. So these are actually, as and when required, we are going to use all these relations. So with respect to the central forces or actually the planetary motion or the Kepler's laws, these are the concepts, that's what we need. Got it? So from this actually, to conclude, what we have learned is, that is the central orbit is u plus d square u by d theta square equal to capital P by h square u square. This is the law of central orbit or actually the path of the central orbit. And the same thing you can express as 1 by p cube into dp by dr is equal to capital P by h square. So this is again the same central orbit equation in the pedal form. So this is polar, assuming u is equal to 1 by r, and this is the pedal. And then the peripheral velocity is expressed as v square is equal to h square into, so what is the peripheral, h square into u square plus du by d theta whole square. So this is a peripheral velocity. So this peripheral velocity where h is the angular momentum. So this is r square d theta by dt is the value of h. And then the aerial velocity of the planet is half of the angular moment. This is what we proved already. So half of the angular velocity, so half of the aerial velocity, sorry, half of the angular momentum is equal to the aerial velocity, which is dA by dt is equal to h by 2. Right? So this is the summary of the entire discussion. And the planets, actually it obeys the Kepler's laws. Every planet tries to rotate in an elliptical orbit with Sun as one of the focus. And the second law is every planet, the radius vector joining from the Sun to the planet swipes equal areas in equal intervals of time. That is, the aerial velocity is constant. And the third one is T square by R cube is always constant for any planet where T being the time period of revolution and R being the semi-major axis length. This actually I am going to prove with one example. Yeah. So semi-major axis length. So these are the three important Kepler's laws. So which are the governing rules for any planets. Got it? So from these relations, and then so for any central orbit, actually we have derived two different properties for a central orbit. So the properties are, one is angular velocity is constant. Constant for any planet or actually any central orbit. And then the second important rule is, angular momentum, not the velocity. Angular momentum for any central orbit is always constant. This is one important rule. And another important rule is the path of any central orbit. Any central orbit is always a plane. So these are the two important fundamental properties of any central orbit. From these central orbit rules, actually we tried deriving the Kepler's laws and these rules. So these are the fundamental governing rules which we have got it from the movement of any planet or any random particle which is moving in a plane. Got it? Yeah, so yes, UPSC actually sometimes actually asks the derivation. From there actually they will ask the questions. So you should understand these derivations. But if you understand these derivations, that is sufficient enough to solve any kind of problems. Got it? Okay. So this is the entire summary of the central orbits what we have learned. Now actually we are going to use these formulas now to solve some of the problems based on this understanding. Do you have any questions on this? Any questions or any conceptual understanding? Great. So then actually I would like to stop the class for today. In the next class actually for an elliptical orbit or actually any planet actually, if it is rotating, either it is an elliptical orbit or hyperbolic orbit or a parabolic orbit, right? So we will try to derive these relations. That is the peripheral velocity, how much it is going to be, and what would be the path or what would be the law of path. So all those things we are going to derive based on these formulas, whatever I listed out. Got it? Yeah. So that's all for today. Yeah. Thank you. Good night.